Hello everyone! Welcome again to my presentation. Welcome to my YouTube channel. Our topic is all about MRI Basic Principles. MRI Basic Principles. Magnetic resonance is a measurement technique used to examine atoms and molecules. It is based upon the interaction between a applied magnetic field and a particle that possesses spin and charge. This arrangement is analogous to a bar magnet in which the magnetic field is considered to be oriented from south to north pole. From south to north pole. Nuclear spin. All atoms are made up of electrons surrounding an atomic nucleus which can contain protons and neutrons. The structures of an atom is an essential component of MRI experiment. Atoms consist of three fundamental particles: protons, which possess a positive charge; neutrons, which have no charge; and electrons, which have a negative charge. The characteristic chemical reactions of elements depend upon the particular number of each these particles. The properties most commonly used to categorize elements are the atomic number and the atomic weight. The atomic number is the number of protons in the nucleus and is the primary index used to differentiate atoms. All atoms of an element have the same atomic number and undergo the same chemical reactions. The atomic weight is the sum of the number of the protons and the number of the neutrons. Atoms with the same atomic number but different atomic weights are called isotopes. Isotopes of an element will undergo the same chemical reactions but at different reactions rates. The nucleus of an atom can have quantum property known as nuclear spin. A rotating nucleus, this one, with a positive charge produce a magnetic field known as the magnetic moment oriented parallel to the axis of rotation. For instance, a hydrogen atom has a protons as its nucleus and the magnetizations from a microscopic sample of proton spin is what is commonly measured in nuclear magnetic resonance and magnetic resonance imaging. Many atoms have nuclei with the property because hydrogen is the key component of biological tissue, which is water and fat, and most commonly visualized in clinical MRI. In the absence of externally applied magnetic field, the nuclear magnetization is randomly oriented. In other words, the magnetizations from each proton in a group of protons, that is, in a cup of water or the human body, is not aligned. However, in the presence of the external magnetic field, such as the use in nuclear magnetic resonance or magnetic resonance imaging, the nuclei act like tiny bar magnets and align themselves with the field in one of two states, parallel or anti-parallel. The state parallel to the external magnetic field has a slightly lower energy level than the anti-parallel state. So slightly more nuclei end up in the parallel state than in the anti-parallel state. For clinical magnetic resonance imaging field strengths, only one or two protons in a million can be detected. This number increases as the MRI field strength increases, which leads to an increase in the signal to noise ratio at higher field strength. Nuclear magnetic resonance. The net magnetizations of protons in an external magnetic field aligns with the external magnetic field. This is called the equilibrium state of the magnetization and is usually defined as Z direction. However, by the applying energy in the form of electromagnetic waves at precisely the right frequency, the net magnetizations can be made to tip away from equilibrium position in the x to y plane. This frequency is known as Larmor frequency. This equation. This symbol is the precession frequency, and this symbol is a constant that differs for each atomic nucleus known as gyromagnetic ratio. And this one is the strength of the external magnetic field. For instance, protons with a gyromagnetic ratio of 42.577 MHz per Tesla or 38 in a magnetic field of 3.0 Tesla will be tipped when energy with a frequency of 127.731 MHz is applied. This energy is transmitted by so-called transmit coils and is usually referred to as a radiofrequency pulse. The angle by which the magnetization is tipped is called the tip angle. Once displayed from equilibrium, the net magnetization will precess around the external magnetic field. Before excitation, the magnetization is aligned along z-axis, the red arrow. After a 90 degrees radiofrequency pulse, the magnetization is tipped into the xy plane. Here it is shown as being aligned with the x-axis, the orange arrow. Once in the xy plane, the magnetization begins to precess in the x to y plane, first moving between the x and y axes, the yellow, first moving, the yellow arrow, and then aligning with the y-axis, the green arrow, and after a longer time pointing in the negative direction along the x-axis, the blue arrow. The magnetization will eventually precess around the x-axis again and continue to move around in the x to y plane. Note that the effect of 180-degree pulse would be to completely invert the magnetization, the purple arrow. Signal can only be picked up the magnetization that is precessing in the y to x to y plane. Signals. An radio frequency receiver coil is used to collect the signal after it is tipped into plane using an radio frequency pulse. In simple terms, the receiver coil sees magnetization along one direction. In other words, voltage is induced in the receiver coil because of the change in directions of the magnetization's vector that result from the precession, similar to an electrical generator. The signal collected from the receiver coil along the x direction. Immediately after the RF pulse or radio frequency pulse, the signal along the x direction is maximal, leading to a large signal, the orange dot. As the magnetization process, the signal decreases, this one, the yellow dot, until it reaches a minimum when the magnetizations point along the y directions, the green dot. The magnetization continues to process, leading to a negative signal when it's pointed in the negative x direction, the negative. This is the blue dot. Continued precessions leads to the sinusoidal signal shape over time. sinusoidal shape over time. Relaxation. T1 relaxations, otherwise known as spin lattice relaxation or longitudinal relaxation. A plot showing the T1 relaxation of two tissues, this one, the red curve and the black curve, with a different T1 values after a 90-degree radiofrequency pulse. Immediately after the pulse, the longitudinal magnetizations is zero because all of the magnetization points along the x to y plane over the time the magnetization slow returns to equilibrium. The curve shown in the black describe this one, the relaxation of tissue with a long T1 value 1000 milliseconds. Note that it is take a long time for magnetization to return back to equilibrium value. The red curve describe the relaxation of tissue with a short T1 value, 200 milliseconds. This curve shows the longitudinal magnetization is restored more quickly. So, the more quickly is this one, the red curve. The tissue with the shorter T1 requires less time for the protons to return the equilibrium state that is aligned with the z-axis, whereas the tissue with a longer T1 time relaxes more slowly. This difference in T1 times can be used to generate contrast in MRI images. Gadolinium-based contrast agents are often injected into the blood pool to shorten the T1 time of blood and or perfuse tissues, which given appropriate pulse sequence settings can cause a large difference between signals from tissue in the proximity of the contrast agent and the other tissues unaffected by the contrast agent. Next is T2 relaxation, otherwise known as spin-spin or transverse relaxation. A plot showing T2 decay from two tissues with different T2 values. This curve, the red curve and the black curve. Immediately after a 90-degree RF pulse, again, all the magnetization is found in X to Y plane. As the spins process, they start to debase, leading to decrease in the net magnetization to T2 decay. The red curve show the signal time curves for a tissue with a long tissue value, 200 milliseconds, and the black curve, this one, is show a tissue with a short T2 value. The signal coming from the tissue with the shorter tissue decays faster, and this effect is used to generate T2 contrast in MRIs. Okay, the smaller the T2 value, the faster the magnetizations fans out around the X to Y plane. Okay, this is the shorter tissue, 50 milliseconds, leading to a rapid decrease in the signals. Like T1, different tissues have different T2 values depending on the makeup of the tissue. Small disturbances in the local magnetic field of the tissue can cause rapid T2 decay as well as differences in the chemical environments. In broad sense, T2 provides information about how fluid-like particle tissues. Solid tissues have shorter T2 values, whereas pure liquid water has very long T2 value. It is important to note that the T1 and T2 times of tissues are not mathematically related, and MRIs often weight by one or both of these parameters to highlight desired structures. However, T2 is shorter than T1. Repeat, T2 is shorter than T1. Okay. Okay, that's all for today. I hope you gained some knowledge in this video. Hope you like it. Please like and subscribe for more updates and topics. Thank you for watching.